Hello everybody, welcome back. Now we're starting on something new and exciting. We're doing anti-differentiation. So we've talked about derivatives and where they come from and what we can use them for and how that's all important and connected to slope, all those really cool ideas. But now we're going to do the process in reverse. So historically, we usually think of calculus as coming in two pieces. There's differential calculus, which is calculus about derivatives and the things we've already done. And then there's integral calculus, which is about going the other direction. It's about starting with a derivative and going backwards and all the cool things that we can do with that. So let's talk about that for a second. So anti-differentiation really means reversing the process of taking a derivative. So a function capital F is an antiderivative for a function little f if capital F prime is little f. Okay? So in other words, if you start with a function little f, right, we don't want to take its derivative now. What we want to do is pretend it was the derivative and find out where it came from. For example, let's say that little f is 2x. Okay, little f of x is 2x. Where did it come from? Well, obviously the answer's got to be x squared, right? Because if I took the derivative of x squared, then you get 2x. So in this case, our antiderivative, our capital F, is the notation we're using here, will be x squared. But if you think about that for a second, let me give you another antiderivative. What about x squared plus 3? I'm calling that capital G of x to give it a different name, right? And to be cute, because, F and then G and so forth. But what happens if I take the derivative of x squared plus 3? Well, obviously I'd get 2x, and then the 3 would go away. So what happens, of course, when you take a derivative is anytime there's a constant, the constant becomes 0 when you take the derivative. So I like to describe it this way. When you have a function and you come along and you differentiate it, so you have this perfectly nice function that was minding its own business, walking down the sidewalk, and somebody came along and differentiated it, and they're just laying out there now, horribly differentiated all over the sidewalk. So when the differentiator does that, they steal any constant that was left over. So when CSI shows up, right, or NCS or whatever your favorite crime drama is, to try to reconstruct the scene here and to figure out what function this was before it got horribly differentiated, and the constant's missing because it turned into 0 and it's disappeared. So the forensics team can never recover what the constant was because it's gone now. It turned into 0 and it's just gone. So here's what we'll do. In general, what we'll do when we find an antiderivative of something, we'll add a plus c at the end, right? Where c is really a placeholder for the constant that got stolen by the differentiator. So in this case, we would write something like x squared plus c. And the plus c is there to remind us that there could have been a constant there, but we don't know what it was without some more information, right, than what we've been given. Just by looking at this horribly differentiated mess laying out there on the sidewalk, we can never, forensically reconstruct what c might have been there. So we use the c as like a placeholder for a constant that could have been there. Okay, so we need some notation now, and this is where we get to do the first time we get to see this symbol and do some really cool things. So that's a scripty S, sort of. This is the historical precedent for why people chose that integral sign, the very first thing you see there. That again, it's like a curve and then a line and a curve at the top. It's supposed to look like a scripty S. Why a scripty S? Well, we'll see that in the next couple of lectures. But it's this strange scripty S looking integral sign, then the function that we want to find an antiderivative of, the f of x, then this dx, and again, the reason for the notation we'll find out soon enough. But for right now, you can imagine that integral sign and the dx as forming like the beginning and the ending of the thing we want to anti-differentiate. Okay? Then we take the blue little f of x, we find the antiderivative for it, call it capital F, and then add the plus c to the end, because again, we have to have that placeholder. You've written this way, we'll often call this an indefinite integral. So an indefinite integral is just another name for antiderivative. We'll talk about other uses of the word integral in the next few lectures, and the reason for the notation will become obvious then. But for now, all we mean by this is antiderivative. If we wanted to read this with English, we would say things like, this is the indefinite integral of f with respect to x. Now, I mention this because sometimes we rush through this in our haste to get to homework problems, right? And start doing integrals. We're trying to do the kinds of things we'll see in the homework. And we'll do plenty of examples of that in just a second. But let me make sure that I've at least said this so that you understand what the with respect to x means, because you'll often see directions that will come up later that will say integrate this with respect to x, or especially in the first part of Calculus 2, you'll very often see word problems with integrals that will say do this integral with respect to x, or do this integral with respect to a different variable. And what we mean by that is just that that's the variable that's in our problem. Okay? The dx at the end is tipping us off as to what the variable in the problem should be. Okay, so if we had to give the various pieces of this other names, and we will, so that we can call them things we need to, that little f of x, the thing that we're finding an antiderivative for, or finding an indefinite integral for, same word, we call that the integrand, the thing that's getting integrated. The dx, of course, tells us what variable we're using to do our integration. That's what the with respect to x means. Of course, that capital F, that's our antiderivative. And the c, that's the constant that we'll always have when we do an indefinite integral, because we can't tell what constant might have been there. Okay, our procedural rules for finding integrals on this slide is truthfully really boring. And if I didn't tell you this, you would assume this was true anyway. But I'm a mathematician, and so I'm contractually obligated to explain this to you. So let's look at this first rule for a second. C, this little c, little small c there, that's just a constant. Right? And in this case, I'm doing my integration with respect to u, just again to change things up so that you get used to seeing different variables. Notice the du there tells me that u is supposed to be my variable. So I'm integrating with respect to u. Again, just to be different so that you don't expect to always see x's, because we won't always have x's. But what happens between the left-hand side of this equation and the right-hand side of the equation is that I've just taken the c and moved it outside the integral sign, right? So now the c has moved. Well, why can you do that? What does that really mean? Well, again, this is just an obvious derivative rule, but backwards. How do you take the derivative of a constant times a function? Well, you just leave the constant sitting there in front and then take the derivative of the function, right? In other words, the derivative of a constant times a function is still the constant times its derivative. You just ignore the constant, just leave it sitting there in front, right? It's the same thing that happens with an antiderivative, of course, because it's just the same procedure, but backwards. So if you want to integrate a constant times a function, you can just write down the constant and then find the antiderivative for the function. The same thing happens when you take a derivative, right? If you have two things added together and you want to take their derivative, you do the first derivative, then a plus sign, then you do the second derivative, or the derivative of the second function, I mean. This next rule I've displayed says the same thing has to work for antiderivatives. If you have two things that are being added together and you want to find the antiderivative, you just do the antiderivatives for each piece and add them together, which is obviously what you would have done without thinking about it, had I not said anything. But again, as a mathematician, I sort of have to tell you the rules. Subtraction obviously works the same way. And if we put both, or maybe all three of those together, then if you have a constant times a function, plus or minus, either way, a constant times another function, you could do that in the obvious sort of way. You just write down your constant, then multiply it by whatever you get for the antiderivative of the first function. Then again, plus or minus, whichever one you happen to have had before. Then the second constant, and then the antiderivative before. Just like you would do when you were taking a derivative without even thinking about it. The same thing works in reverse when you do an antiderivative. Okay, so just like we had this huge number of derivative rules, we now have a very large number of antiderivative rules. And they're They're the same rules, but backwards. So, for example, one of the first things we learned when we took a derivative is how to take the derivative of u to the n. Again, I'm going to integrate with respect to u here just to be different so I don't always use x's. If you have u to the n and I took the derivative, I would bring the u down in front. In other words, I would multiply by the n, and then I would subtract 1 from the exponent. Well, antidifferentiation is the same thing, but backwards. So instead of multiplying by n and subtracting 1 from the exponent, I do exactly the opposite and in the reverse order. So again, instead of multiplying and adding 1, I add 1, multiplying and subtracting 1, I add 1 and then divide. In other words, I have u to the n, it becomes u to the n plus 1, because I have to add 1 to the exponent, and then divide by the n plus 1. Okay? And then, of course, add my constant c, and we're good to go. Now, if you think about this for a second, what would happen if I took the derivative of u to the n plus 1 divided by n plus 1? Well, that n plus 1 would come down in front and cancel with that n plus 1 that I've divided by, so I wouldn't see that anymore. And when I subtract the 1 from the exponent, I get back to u to the n. Well, okay, so if you're reading along on the screen there, you'll notice that there's one caveat to this rule, and that is this doesn't work when n is equal to -1. So let's think about what would happen. If n were equal to -1, then when I added 1 to it, I would get 0, and now I'd be dividing by 0. So, explosions into the world. Ah! Okay, that's not going to work. So, what's really going on when you have n equal to -1? Well, when you have n equal to -1, you'd have u to the -1, which is 1 over u, and obviously the antiderivative for that shouldn't be another u raised to a power. Where do you get 1 over u? What's that the derivative of? Of a log. Right, so we'll see how that plays out in just a second. But before we do that, let's do an example to make sure that the first formula was sort of clear how this would work. So if I wanted to find the antiderivative for x to the 5th, okay? So again, the derivative, we know how to do that. We bring down the 5, multiply it, and we add 1 to the exponent. Subtract 1 to the exponent. Now we're going to integrate. Now we add 1 to the exponent and divide. So what we get is x to the 5 plus 1, and we divide by 5 plus 1, which of course gives us x to the 6th over 6. And we always add our friend the plus c, again, as a placeholder for that constant that we can't ever know what could have been there if all we know is that the derivative was x to the 5th, and we try to reconstruct the original function. And of course, we can check our work, because if I start with x to the 6th divided by 6 and take the derivative, I'll bring down that 6. It'll cancel with the 6 in the denominator, so I don't see that anymore. And now I have x to the 6th minus 1, which of course is 5, and I get back to x to the 5th. So one of the nice things about doing antiderivatives, doing these indefinite integrals, is that because we're so good at taking derivatives now, we can always check our answers. Okay, so I mentioned before when n was equal to -1 in that rule, this rule doesn't work anymore. And the reason is because doing u to the -1 is really doing 1 over u. And that should be the antiderivative for what? Not u raised to a power, but for a log. Okay, but there's something weird about the way we just wrote this on the screen. I wrote log of absolute value of u. Of course, plus c. The plus c isn't weird. It's the absolute value that's weird, or at least weird when you first think about it. So back when we were first taking derivatives, we saw that if you took the derivative of log of absolute value of u, you would get 1 over u. So that does work as the derivative. The reason is because absolute value of u is u. Well, sorry, absolute value of u is just u, right? If u's positive. And it's negative u if u's negative. And when you go through the chain rule and check how to take the derivative of log of negative u, sure enough, you'd still get 1 over u. So why do we put the absolute values here and count this? Well, think about it. What's the domain of 1 over u? What kind of numbers could I plug into that? I could plug positive numbers into 1 over u. I could plug negative numbers into 1 over u. Okay? I could plug anything into there except for 0. So when we find our antiderivative, we want to do it in the most general way possible. We want to allow ourselves to plug the same kind of numbers into our antiderivative that we could have plugged into the original function. So because we can plug positive numbers into 1 over u and also negative numbers into 1 over u, okay, I want to write the antiderivative as log of absolute value of u. Because without the absolute value of u, I'd be trying to take the log of a negative number. And as you remember, we can't take the log of a negative number. But if we put the absolute values in there, then we don't have the log of a negative number because the absolute values will fix the negative before we're done. So the gist of this is always, always, always be careful to put your absolute values in there. Okay, so that was logs. Maybe the easiest formula ever, right, would be how do you do the inverse of a log? How do you do the inverse, or how do you do an antiderivative for e to the u? Well, obviously, if I've got e to the u, and I say, you know, that's my function, that's my derivative, right? What could it have possibly come from? Well, obviously, just e to the u itself, right? Integration and differentiation, neither one affect e to the u. Still just e to the u. Okay, so again, we need lots of examples here. So here's one. X squared plus 4 x cubed. And we had that discussion a few minutes ago about the rules that say that we can just do this the way we normally would without even thinking about it. In other words, we'll find the antiderivative for the x squared, then write down the plus sign, then find an antiderivative for the 4x cubed. Okay? So what would be an antiderivative for the x squared? Well, I'd add 1 to the exponent and divide, which again is exactly the opposite and in the opposite order I would do if I were taking the derivative. So adding 1 to the exponent would give me x cubed, and I'd divide by the 3. Now with the 4x cubed, I would add 1 to the exponent. That'd give me x to the 4th, and I'd divide by 4. And leave the 4 outside, or just cancel it with the 4 that would be in the denominator. So I get x to the 3rd over 3 plus x to the 4th plus c. And of course, obviously, looking at 4x cubed, you would go, oh, I recognize that. That's clearly the derivative of x to the 4th. What about 3 over x? Well, 3 is just a constant, so I can write down the 3 and then find an antiderivative for 1 over x. And as we said, the right way to take an antiderivative for 1 over x isn't just log, it's log of absolute value of x plus c. What about 5 times the square root of x? Well, okay, how do I find the derivative, of a square root, right? We remember that the first step is going to be to take that square root and to turn it into exponential notation, right? Write it as x raised to a power. So then I have a rule I can use. And of course, the square root of x would be x raised to the 1/2 power. Now I just use my power rule. So I get the 5 times x raised to the 3/2 power over 3/2 plus my c. And if I want to do a little arithmetic, like take that 3/2 of the denominator and flip it and bring it up, I could multiply my 5 by 2/3, which would give me 10/3 in front if I wanted to do a little extra arithmetic. Okay, so this one looks a little weird because it looks like a fraction. X squared plus the 4th root of x plus 7 all over x squared. Normally, when you see a fraction like this, you kind of want to freak out because it's like, oh, wow, that looks like it may have come from a quotient rule, right, to be a fraction like that. But, well, it didn't, or at least it doesn't have to have, right? We can work our way around that because we can use just a little bit of algebra to split this up. So, see, what we can do is make this, because there's just an x squared in the denominator, I could make this with each of the terms in the numerator divided by x squared and add all those up. In other words, I make it x squared over x squared plus the 4th root of x over x squared plus 7 over x squared. Okay? So in other words, x squared over x squared is just 1. The 4th root of x over x squared, well, if I do that and simplify it a little bit, that becomes, with the x squared, that if I bring that to the top, that becomes negative 8/4. So when I combine x to the negative 8/4 with x to the 1/4, that becomes x to the negative 7/4. And then I have plus 7 over x squared. But again, that's gross to try to take an antiderivative for. I need to make that x raised to a power, So 7 over x squared, I turn that into 7x to the negative 2 power. So I've just rewritten it with just a little bit of algebra. I haven't done any calculus yet. I've just rewritten it with a little bit of algebra in such a way that it's much, much easier to deal with, right? Because now I just have x's raised to powers. So I can just hit it with the power rule. When I have a 1 and I need to find the antiderivative, obviously that's just going to be x, right? Because how would I have gotten 1 as a derivative? It would have had to come from an x. Then x to the negative 7/4, well, I add 1. Okay, great. Now I got to do fractions. So negative 7/4 plus 1, I'll have to make that plus 4/4. So negative 7/4 plus 4/4. I do the arithmetic and that comes out to negative 3/4. Then divide by the negative 3/4. Now I've got x to the negative 2 power. So I'll have to add 1, make that x to the negative 1 power divided by the negative 1. Still leave the 7 multiplied in front, and don't forget to add our plus c because we have now done an indefinite integral. I found an antiderivative, so I should always have the plus c at the end. Okay, we have all these various trig things that we've learned, right? And we can just use the derivative rules we've always known to write down now antiderivative rules. So, for example, what about the integral of sine? Well, if I saw sine as a derivative, what would it have to come from? Well, first guess you might think cosine, but actually that doesn't quite work because remember the derivative of cosine is negative sine, so there ought to be a negative sign in there. So in other words, in order to handle the fact that I just had a sine, the right antiderivative would be negative cosine. And now if we think about this going from right to left, in other words, if I take the derivative of negative cosine, I'll get negative sine, and the two negatives will cancel out, so I get back to sine. Okay, just doing cosine is a little easier because the derivative of sine is cosine. So there we go. What about secant squared? Well, obviously that's sitting there because we know that's the derivative of something. Secant squared is the derivative of tangent. Okay? And then cosecant squared. Well, again, that's the derivative of something that we know. Usually there'd be a minus sign with that, but we don't have to do that. We can do the same trick we did with cosine. Instead of making this cotangent, which is normally what you would expect to see, lurking in the background if you see a cosecant squared sitting there, it'll be negative cotangent, right? Because if I take the derivative of cotangent, I would get negative cosecant squared. So if I take the derivative of negative cotangent, I'll get negative cosecant squared. The two negatives cancel out, and I get the cosecant squared I was looking for. Okay. What about secant tangent? Secant of u times tangent of u. Well, obviously that's sitting there waving its arms going, hello, I'm the derivative of a secant. And sure enough, you are. So an antiderivative for that would just be secant of u. For cosecant of u, cotangent of u, that's sitting there looking like, yep, I'm the derivative of a cosecant, except again, we'll need the extra minus sign. Okay, what else? Well, we know other derivative formulas that we can now rewrite as antidifferentiation formulas, or indefinite integral rules. So 1 over the square root of 1 minus u squared, that's obviously what? The derivative of inverse sine. So when we find an antiderivative for that, it'll be arc sine, inverse sine of u. Because here we're integrating with respect to u. Again, I'm switching back and forth between u's and x's on purpose just to make sure we don't get used to seeing things one way and have it freak us out when we see different variables. What about 1 over 1 plus u squared? Well, we look at that for a little bit and we think, seen u before, right? That's what you'd get from taking the derivative of an inverse tangent. And then 1 over absolute value of u, square root of u squared minus 1. That's obviously the derivative of an arc secant. So we have all those old derivative rules that we've learned. Now we just write them in the other order, and we have integral rules. Okay, so what can we do with this idea of antidifferentiation? Well, here's an easy problem that we can use thinking about this in terms of antiderivatives. So I have a function, and its graph has a slope it's 2x at every point. Okay? And the graph goes through up to 0.14. The question is, what's my function? So I haven't told you the function, I've just told you the slope. Okay, so of course, obviously, what I'm really doing there, when I say the slope is 2x at every point, I'm really telling you what the derivative is, right? Because the derivative is the slope of the tangent line. So what's really going on here is I'm telling you the derivative and asking you to work backwards. And that's obviously a job for anti-differentiation man, right? So because the slope is always the derivative, when I tell you that I've given you the slope and ask you for the original function, then we're just going backwards. So I take my 2x, that's my derivative. I say, where'd you come from? Well, you had to come from x squared. Well, almost, right? Because it could have been x squared, or it could have been x squared plus 3, or it could have been x squared minus 17. Because when I take the derivative of x squared plus a constant, the constant disappears. So I don't know what the original constant might have been. As I try to reconstruct this function, knowing only what I see laid out on the sidewalk before me, horribly differentiated, that's 2x. I see the 2x laying there. I'm going, where'd you come from, 2x? Well, you came from x squared, possibly plus a constant. So how in the world could I figure out what that constant was? Well, I've got to have another clue, right? I've got to have somewhere in the crime drama, somebody's got to drop another clue besides just what the derivative is. And here's where the problem says that this graph goes through the point 1, 4. In other words, when you plug 1 into my function, I should get 4. So that little piece of information is enough to let us figure out what the c has to be. Because now I'll plug 1 into x squared plus c, and that should equal 4, right? So I've got an equation now. 4 should equal 1 squared plus c. And now I can just solve, right? 1 squared, of course, that's just 1. I subtract that on the other side. I get that c has to be 3. So my function that I've been looking for all this time, f of x, is x squared plus 3. Okay, let's do this with a little bit of physics. It's the same idea. A particle has an acceleration that's negative 32, right? And I'll leave off the units for now, although in general it's really important to leave units in there. Writing 32, you may guess that the units I am intending here is feet per second squared, right? So the acceleration is negative 32, let's say feet per second squared, and that happens, whenever t is positive, for all positive time. Okay? Then we know that the particle is at position s equal 5 feet when the velocity, and the velocity there is negative 2 feet per second when time is equal to 1 second. Then the question is, where is it when time is 4 seconds? Well, that sounds like a lot of complicated stuff. But let's just write down what we know, and it's very, very easy. Because when I tell you that I know the acceleration, what does that mean? Well, remember, acceleration is the derivative of the velocity. So I can use the fact that I know the acceleration to go backwards and figure out the velocity. The velocity, right, I get from just anti-differentiating the acceleration. In other words, take the acceleration and go backwards, right, to find the velocity that it had to have come from. So if my acceleration is negative 32, then what's an antiderivative for that? Well, obviously negative 32t, right? Because that's what the derivative would have had to be, right? In order to get that's what the function would have had to be in order for negative 32 to be its derivative. And then I'll have to add a constant. Now, I wrote this as plus c sub 1, that little sub 1 is there, because I'm going to be doing this process a couple of times. In just a second, I'm obviously going to take the velocity and go backwards to get position. And when I do that, I'll have another constant. So rather than keep writing plus c, I'm going to write c1 because that's the first c I'm going to have in this problem. There'll be others. Okay, but now I can use the same trick again because I know that when time is equal to 1, the velocity should be negative 2. In other words, when I plug 1 into the velocity equation, I should be able to do the arithmetic and 2 should come out. So negative 32 times 1, I didn't write the times 1 obviously because, negative 32 times 1 is still negative 32. But I get negative 32 times 1 plus this first constant should equal a velocity of negative 2 feet per second. And that lets me solve for C2, right? If I take the negative 32 over to the other side, then C1 has to be 30. That's great. Now I have completely figured out my velocity. It had to be negative 32t plus this constant, which we figured out had to be 30. That's awesome. That's enough then to go backwards a step and figure out the position. Because remember, velocity is the derivative of the position function. So I just say, okay, my derivative was negative 32t plus 30. So I go backwards, right, to figure out what the original function, the original position function, had to be. So now I'm integrating negative 32t plus 30. And again, the power rule just rides to the rescue here. What happens with the negative 32t? Well, I need to add 1 to the exponent. That gives me t squared. Then divide by 2. And of course, that negative 32 is still in front. Now, I've gone ahead and done the arithmetic. Negative 32 divided by the 2, I can go ahead and cancel that and make that negative 16. Right? Then I have plus 30. Well, obviously, if that's a derivative, where did it come from? Well, the original function had to have been 30t, right? Plus some other constant, okay? And I'll call that other constant C2 because I've already used, well, C1, right? Now, the other thing they told me in the problem was that the position of this particle is 5 when t is equal to 1. In other words, when I plug 1 into this equation, I should get 5. So I'll do that. I'll do negative 16 times 1 squared plus 30 times 1 plus C2. Again, I didn't write the 1 squared and the times 1 in there because obviously, that's already simplified. You know what happens when you multiply something by 1. But when you do all of that, plugging 1 into the equation, you should get 5. Well, that's enough now to solve for this C2. Right? If I do the arithmetic and solve for the C2, you get negative 9. So finally, it tells me my position function should be negative 16t squared plus 30t plus my constant, which was negative 9. And finally, now we've reconstructed the velocity, we've reconstructed the position, and the thing that the question was asking for all along was, where's the particle when t is 4? In other words, what's the position when t is equal to 4? That would be s of 4, so I plug 4 into the position equation, and when you do the arithmetic and simplify all that, you get a negative 145 feet.